Hello and welcome to Brunei Math Club. In this video, I'll explain the following fact. Let A be an m by n matrix. Then there are square matrices Q1, Q2, and so on up to Qs such that this product, that is A times Q1 times Q2 times and so on up to Qs, this is the reduced echelon form of the matrix A. These matrices are called elementary matrices, and each of them corresponds to an elementary row operation. Okay, let's start. First, let's consider some examples. Let's take this matrix and we want to swap its second row and the third row. To do that, we can multiply this matrix from the left. Then we get this. Indeed, the second row and the third row, they are swapped. Look at this matrix. This is similar to the identity matrix of order 3, but except that the second row and the third row are swapped. Similarly, if we want to multiply the first row by a constant c, then we can multiply this matrix from the left. Again, this matrix is similar to the identity matrix, except that the first row is multiplied by c. Then if we do this multiplication, we get this result. Indeed, the first row is multiplied by the constant c. And next, we want to add to the first row the third row times some constant a. To do that, we multiply this matrix from the left. Again, this is similar to the identity matrix, except that its 1,3 element is a instead of 0. So if we do this multiplication, we get this result. Indeed, the third row times a is added to the first row. Of course, the third row is unchanged. Now let's define the elementary matrices more formally. So we have three kinds of elementary matrices, that is swapping two rows and multiplying one row and adding to one row a multiple of another row. So the first thing is swapping the row I and the row j. That matrix is denoted by Pij, that is defined as this. Here, this is almost identical to the identity matrix except for the ith row and the jth row. And so all the diagonal elements are 1 except for this and this. So the ith row and the jth row. And for these rows, instead we have 1s here in the off-diagonal elements. So this is ij element and this is ji element. Multiplying this matrix from the left swaps the ith row and the jth row of a given matrix. And next is multiplying the ith row by some non-zero constant c. And that matrix is denoted by Pi of c. So this is similar to the identity matrix, except that this element is c instead of 1. So this is the I element of the matrix. Multiplying this matrix from the left will multiply the ith row of a matrix by the constant c. And lastly, consider this elementary row operation, that is adding to the ith row the jth row times a. This elementary matrix is denoted by this Pij of a. And it is almost the same as the identity matrix except for this element, which is the ij element of the matrix. Instead of 0, we have a here. A is this a. So if we multiply this matrix from the left, then we have this elementary row operation. Now let's see how these elementary matrices actually work. So let A be an m by n matrix whose elements are these. And we have just defined these elementary matrices. First try this one, Pij. So that swaps the ith row and the jth row. So we have this matrix. I just omit other elements. So all the diagonals are 1s except for this, and this one is ij element, and this one is ji element. And this is the ith row of the matrix A, and this is the jth row. So if we apply this, then we get this. So now the ith row becomes the original jth row, and the jth row becomes the original ith row. So these rows are swapped. And next try this matrix. So pi of c times a, and pi of c is this matrix. This is almost the same as the identity matrix except for the ith diagonal element, which is c. And this is the ith row of the matrix A. So if we multiply this, then we have this. The ith row becomes scaled by c, and all other rows are unchanged. Lastly, consider multiplying the elementary matrix Pij of A to the matrix A from the left. So Pij of A is this matrix, which is identical to the identity matrix, except for its ij element, which is A instead of 0. And we have the ith row and the jth row of the matrix A. And the result is this. So the ith row has been changed, and the jth row is unchanged. Let's look at this multiplication a little bit more closely. So to get, for example, this element, which is I1 element, we multiply the ith row with the first column, right? So in the ith row, all the elements are 0 except for the ith element and the jth element. And the ith element is multiplied by this, and the jth element A is multiplied by this. So we get this element. And same for here and here and here. This is how we get this result. So multiplying this matrix corresponds to this elementary row operation. In summary, all the elementary row operations can be translated into multiplying these elementary matrices from the left, whether it's swapping or multiplying or adding. Next, let's see an example of applying a series of elementary matrices from the left. First, consider this matrix A. So it's a 3 by 4 matrix. Then first we apply P12, which swaps the first row and the second row, and we get this. So the first row becomes the second row, and the second row becomes the first row. And to this matrix, we again apply another elementary matrix, P21 of -1. So this adds to the second row, the first row times -1. So to the second row, we add -1 times the first row. So -1 times 1 is -1. So if we add to 1, we get 0. -1 times 1 is -1. We add it to 0, and we get -1, and so on. And for this, we get -3. And for this, we get 2. And then to this matrix, we apply P31 of 1. So that means we multiply the first row by 1 and add it to the third row. So 1 times 1 is 1, and add it to -1, we get 0. And 1 times 1 is 1, add it to 3, we get 4. 1 times 1, add it to -5, we get -4. And 1 times -1 is -1, and add it to 0, we get -1. And to this matrix, we apply this matrix, and so we get this. And again, to this matrix, we apply P32 of -4, we get this. So here we get an echelon form of the matrix A. So if we continue this process with appropriate choices of elementary matrices, eventually we can get the reduced echelon form of the matrix A. Hence, we present our final result of this video. For any n by n matrix A, there exists a finite number of elementary matrices of order m, q1, q2, and so on, such that this product, A times q1 times q2 times and so on times qs, is the reduced echelon form of A. The proof of this theorem is quite trivial, I think, because we know that any matrix can be transformed into the reduced echelon form by a series of elementary row operations, and each elementary row operation corresponds to multiplying an elementary matrix to the given matrix from the left. So if we continue this multiplication from the left over and over, we eventually get the reduced echelon form. And we are done. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.